Okay, so a very beautiful day once again. So just pick things up from where we stopped. We reviewed signal classification last time, and this time we'll be looking up signal manipulation. And in our last class, we were able to classify quite a number of signals and equally played with specific applications. You know, we made mention of the realization of revalued signals, discrete Fourier transform and fast Fourier transform optimization, and linear phase filters using conjugate symmetric signals. And then we also mentioned that the conjugate antisymmetric signals could be used to realize odd signals. And I want to mention that they could also be used to achieve Hilbert transforms and phase manipulation. Then we also talked about periodic signals and aperiodic signals. We know that periodic signals are used in communication as for carrier waves. They are used in OFDM. They're also used for, as AC power, musical tones. What else again? System frequency response. While the periodic signal are used for pulse modulation. They are used in sonar, radar, speech processing, seismic signals. And what else again? System transient response, yeah, for a periodic signal. So when we talk in terms of applications, and then we also made mention of energy signals, which are commonly used in digital communication, pulse modulation, radar signal detection, and power signals, which are mainly used as carrier signals. They are used in broadcasting, noise analysis, pulse spectral densities, Then I think we also made mention of neither energy nor power signals. And we made mention of a few types, the ramp signal, which you already know, which has infinite energy and power. So they are used for system response analysis. They are used also in control systems. Then we also have another neither energy nor power signal, the exponential signal, which we commonly find being used in financial modeling, your stock market and all of that. Then even population dynamics. Then we have chirp signals, which are used for sonar, radar, even communication systems too. Then we also have the Dirac delta, which is where we will see that a lot, impulse response, okay, for convolution and the likes. Then we also have the sinusoidal signal, where we say sin t, which is a theoretical infinite duration signal. We see that it is used in Fourier analysis and modulation techniques. So we mentioned, all of those, talking about signal classification and what have you. So this time we are going to go way into signal manipulation. So how do we play with these signals? When we see them, how do we, analyze them? Okay. 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 Now, if you already looked up the notes, you see that we made mention of a few things. We'll start from your regular arithmetic operation, where we can perform addition, we can perform subtraction, we can also perform multiplication. Then even division. Then we can move on to time scaling. Then which other operation do we consider? We have time reversal. Then we have amplitude scaling. Then we also have amplitude reversal. And then time shifting. Then amplitude shifting. So I think we are going to be talking about these operations. Then afterwards, we can now play with some other activities in terms of representing your waveform. Okay. Now, when we talk about your addition, subtraction, multiplication, it follows directly from, what we already know. Okay. So we want to put up the time scale in a chart, then we want to play with the amplitude values over that chart. So let's assume I have a signal, say like this. Let's be more precise. So let's assume this line. I have this line. So let's have this line. Then I have this line. So let's assume I have a signal that probably comes this way. Okay, so we have that signal. And then let's say we have another signal that comes all the way, say from this point. Comes this way. Then it goes this way, and it's not straight. Then we say it goes this way. Then it goes this way. Then it comes this way. So in other words, I have a point here. Okay. Let's come back to this and then this. So it means for this, say this is -2, -1. Say this is 0. So let's say this is -2, -1, then this is 0, right? So it means that at -2, I have a point here. At -1, I have a point here. No. At -1, I have a point here. Then at 0, I equally have a point here. So let's assume this is 0, 1, 2. Then this is 0. So let's say this is 2. Okay. So I have 2 plots here. So this is my S of 1t, and this is S of 2t. This is my time axis. This is my time axis. So Means at -2, okay, let's say this is -1 here. So this is -1. Then at point -1, so it is 2. Then at point 0, I have a point here, right? So this is what I have. So I have, you know, 2 signals. So I want to perform addition and subtraction. So it is pretty straightforward. So we should be able to resolve these 3 points from this. Okay, let us chat up again. Let's just provide a chart like our graph. So let's extract the data. So we have our time axis here, then we have x1, s2, then we are performing addition, subtraction, and then multiplication here. Okay. Perfect. So I have -1, -2, -1. So let us get this. So we have the time axis. So let's say this S1 of t, this S2 of t. So I want to perform addition here. Addition, I want to perform subtraction here, then I want to perform multiplication here. Multi, okay? Then, well, in this time axis, I have -2, -1, and 0. So it could go on and on, okay? It could go on and on, just for this, strictly for analysis. So let us complete this. So separate this from this. Okay. Now, let us extract the data. So can we do that together? So I need someone to tell me. So for x1 of t at time t being the same as -2, what's the value?
-1.
Is that
No,
minus?
1.
Okay.
1.
Okay. At -1?
It's still -1.
2.
Okay, 2, right. Someone said it's -1. You know why it is 2, right? So we plotted at this point, then at -1, we plotted at this point, right? So which is 2, right? So at 0 is what?
0.
At
2.
0,
2.
Oh,
at
sorry.
0 is what?
0.
Is it 0 or 2?
2.
Yeah, it didn't drop. Now, if the signal had dropped, now this one dropped, right? You can say the blue dropped, but this did not drop. So I'm sure this is going this way, okay?
How do you know when it doesn't drop, sir?
Well, that's why I indicated the points, the plots, okay? So usually you see the graph will definitely continue, right? So
Okay, sir.
I think this is one of the examples in the video you already have online. So it's a continuum. So, but well, I had to indicate because it's not dropping. Okay.
Okay, sir.
Yeah, but this one is dropping because this signal probably goes on this way, right?
Yes, sir.
Or it could even come all the way, then go this way. So
Thank you, sir.
You're welcome. So this is 2. So let us extract for S2 of t. So at -2, what do we have? What's the value?
-1.
-1.
1. And at -1 is what? At
2.
It's 2, right?
2.
Okay.
It's 0.
So at 0 is what?
0.
0.
Okay, at 2 is 0. Okay. So this goes on and on, right? This goes on and on. But that's all we have here. But is this clear? Are we all on the same page on this?
Yes, sir.
Yes, sir. So now let us perform addition. So 1 plus -1 is what?
0.
So 2 plus 2,
4.
2 plus 0,
2.
perfect. So we have our signal. So when we perform addition operation, so this is the signal. So let's perform subtraction. 1 minus minus 1.
2.
0, 2, which of them?
2.
2. Yeah. That's 1 minus minus 1 becomes 1 plus 1. So 2 minus 2 would be what?
0.
2 minus 2, 0. Okay. 2 minus 0 is what?
2.
2. Okay, so let's perform multiplication. 1 times minus 1.
Minus 1.
Then 2 times 2.
4.
2 times 0.
0.
Perfect. So if we now decide to plot the first signal for addition, so what do we get? So we have minus 2, minus 1, right? So at minus 2, we have 0. So this is 0. So at minus 1, we have 4.
Yeah.
So this is 4. Okay. So it means this signal is going to trace this way and then go all the way to 4. Right? Then at 0, it is 2. So it's going to step down to 2. If this is 2, it's going to step down to 2 and go this way, right? Yeah. So this is how the signal is going to look. Is that clear?
Yes, sir.
Now this is for addition. Now for subtraction, at minus 2, minus 1, then 0. At minus 2, the signal is 2. So we plot at 2 here, right? Then at minus 1 is 0. So it comes down to 0. Then at 0, it is 2. So it's going to come back to 2, right? So it's going to trace this way to 2. So this is what we get. Exactly. Now for the multiplication operation. Okay, so what do I do now? Okay, let's minimize this. Now for multiplication operation, this is minus 1, minus 2 rather, minus 1. So at minus 2, we have minus 1, right?
Yes, sir.
So it means that this signal is going to, let's clean this. I'll just put my minus 2 here, minus 1. So it means if this is minus 1, so it means we are plotting at this point, all right? Then at minus 1 is 4. So if this is 1, 2, 3, so let's say this is 4. So we are plotting at this point. So it means this is going to come all the way and go all the way. All right? Then at 0, it comes to 0. So that's at this point. So it's going to trace all the way down. I'm sure this is simple enough, right?
Yes, sir.
Yeah. So no matter how complicated the signal may look, the addition, subtraction, multiplication follows directly. Perfect. So we now have time scaling, time reversal, amplitude scaling, amplitude reversal, time shifting, and all of that. So we'll begin to play with them one by one. So let's do time scaling.
Sir, please can you go back to the previous slide? I want to screenshot.
You want a screenshot? Well, we're going to upload the video, don't worry.
Okay, sir. Thanks, sir.
Yeah, so don't worry. We'll get the video. So now, for the time scaling, what we are trying to do, as the name implies, is to scale the time axis, right? So, you know, in your chart, you have the amplitude scale, and then you have the time scale, right? So what we want to do in time scaling is to scale the time, leaving the amplitude the way it is, okay? So if we have to scale the amplitude, then we scale the amplitude. But this time, as the name implies, is to scale the time scale. And if we do this, we are going to achieve one of two things, either signal compression or signal expansion. So you can imagine a signal that spreads over time. So if we scale this time, it's either we expand this signal, or better still, we compress this signal. Okay, so it's going to be one of two things. So once we are making any adjustment around this time axis, we are either going to be spreading or compressing. Okay, so what do we now imply, or what does this imply? Now, for signal compression, we assume that the signal S of t is fed into a system such that we get our output Y of t. But in this case, there is an operator that operates on the time scale, say beta, such that the output becomes S of beta t. Now take note, this beta is performing time scaling operation. So it's not multiplying the amplitude of the signal. It is multiplying the time component of the signal. So you see it in bracket. So if it is compression, then it means that this beta must be some value that will reduce the time scale. Okay.
You know that.
Even I already started the video, but I never. Yes, exactly.
Someone is talking to us, so let's hear you out. Okay, Zainab, tell us. Zainab Zasifa. Okay, yeah, she's on mute now. Okay. Now, the same thing applies for signal expansion. So we have a signal fed into a system that will operate on it such that the time scale is expanded, such that this being beta t. Okay? But the idea is that the value beta, for it to be able, for this value or parameter to be able to compress the signal, or better still, expand the signal, then it must take on a certain value. So it's either this signal is less than a certain parameter or greater than a certain parameter. Does that make sense yet?
Yes, sir.
Okay.
Yes, sir.
Now,
Yes, sir.
okay. Okay. So now, in terms of operation, it means that whatsoever we have as beta, it is not going to multiply if it multiplies this, beta also multiplies this, then at what value will it compress the signal? So if this signal must be compressed, then beta must be less than 1. Now, if this signal must be expanded or must expand, then beta must be greater than 1. Okay? Now, we take an example. So let us assume that beta is the same as 1/2. So it means this is the same as 1/2 because it is less than 1. So it means that we are going to be dividing our time scale by 2. So it means that we are going to be having for compression, we're going to be having S of t going into a system for which beta is the same. For which beta is the same as 1/2, will give us our output y of t, which is now S of t over 2, right? And if beta, for instance, is the same as 2, so we're going to be getting signal expansion such that S of t fed into a system that operates on it, that operates on the time scale, beta equal to 2, will give us y of t being the same as S of 2t. Okay? So, okay, go ahead, please. Samuel Alozie.
Yes, sir. Good afternoon, sir.
A very good afternoon.
Yeah, you said that if the signal is compressed or beta is less than 1, right? That's our parameter. But if the signal must be expanded, beta has to be greater than 1. That's expansion. What happens if the parameter beta happens to be exactly 1? Does it stay the same? Does yt equal xt, or is there any other result?
Exactly. Now, if it is the same as 1, it means nothing is changing.
Okay.
Yeah, intuitively, because beta t is the same as t. So, from what you just said, y of t is equal to S of beta t, such that S of 1 times t is the same as S of t, which is the same as our original signal. Is that
All right,
correct?
sir. Thank you.
You're welcome.
Yeah.
Yeah, so intuitively, it's the same. It remains the same because nothing is changing. The same, the same reason, most of your holy books always, emphasizes 1. When it says 2 shall become 1, right? Because when it's 1, nothing is changing. Everything is just fine. Now, Adebisi, go ahead, please.
Sir, the question I want to ask is that I'm just asking out of this thing. I want to ask if the beta can be 0.
Yeah, for signal attenuation, we want to block the signal.
Okay, sir.
So you want to block it. Yeah, you talk about signal blocking. So you want it to disappear. Okay. So you don't want to find it in the time scale. Okay, so it means you want to do something to that signal. Yeah, so something must nullify it. You're looking at nullity, right?
Yes, sir.
Okay, now, so we'll progress. So this is the same as 2. Now, we can play with one simple example. Okay, let us figure out something. So let's say we have signal S of t to be this. Okay, let's just think. Okay. That's 0, 2. Let's say 2. Okay. This is what we have. So I want to perform signal compression by multiplying the time scale by 2. So if I multiply the time scale by 2, what do we have? T by 2. I have 1, right? Isn't it?
Yes, sir.
So this is the time axis.
Yes, sir.
This is S of t. So I have 1. So t by 2, which is 2 divided by 2, will give us 1. So it means now my signal just compressed. I just compressed my signal. So this is what I now have. That's now my signal, right? But what if t is the same as 2? So now beta t, which will now be 2t, right? Which is 2 times 2, which is 4. So it means that this time scale, we need to extend. So this is going to be twice this. So let's say this is 4. So it just extended to this, and then this becomes my signal, which is an expanded version of that signal. But you will observe that the operation performed here is on the time scale, right? Does that make any sense, please?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now, if this is clear, then we can move on to time reversal. Let us consider time reversal. Now, the time reversal is a special case of time scaling, where we now have to multiply the time scale by a parameter beta as well, but this time, not just beta, but beta being the same as -1. So in a situation whereby we had the signal 0, 2, 2, S of t, t. Now I want to multiply this time scale, t is equal to 2, but now I want to multiply, I have beta t, where beta is the same as -1, which will be -1 times 2, will now be equal to -2. So it means that I'm going to be having something in this axis. Something in this axis. So I can say -2 is somewhere, you know. So where this is my input, then my y of t happens somewhere here, -2, which goes all the way. So you can see there is a reversal in this signal. Yeah, go ahead, please.
Sorry, sir. Sir, is it possible that it could be this signal is an even or odd signal?
Why not? It could be. It could be. We could do same. We could do same for this, an odd signal. We could reverse it. Okay. We could do same. We could reverse it. Yeah. This even we could reverse it. So it only flips, right? It flips.
Okay, sir.
Now,
thank you, sir.
Yeah, can perform the operation on whichever signal. So, well, your time reversal is as simple as this. So, so it's more like flipping. So right now, our output is somewhere around here, while our input is somewhere around here. Don't forget, S of t was sent into the system, then we got y of t. But this case, beta is the same as -1, such that y of t is the same as S of beta t, which is now the same as S of minus T. Okay? So this is our output. Is that clear? Is that clear, please?
Yes, sir.
Okay. So
Yes, sir.
diagrammatically, this is what we achieve this way. Okay, so the next thing now to do is amplitude scaling. So I want to scale the amplitude now. So I need a little mental shift this time, okay? Now we've been playing on the time scale, as the name implies, amplitude. So we want to work on the amplitude, okay? And recall that when we talked about time scaling, a few things I just wanted to take note of, so you don't get them mixed up. When we mention time scaling, let's put it this way. When we mention time, not scaling. When we mention time scaling, we talked about compression and expansion, right? Now that we want to talk about amplitude, so we're not going to be talking about signal amplification and attenuation. Okay, so it's either we want to attenuate the signal or we want to amplify it. Okay, depending on what we want to achieve. So while time scaling, with time scaling, we could achieve compression and expansion. With amplitude scaling, we can achieve amplification and attenuation. So let us take our basic example, as always, this, where this is 2, this is 2, and this is 0. So this is T, this is, okay. I want to extend that axis. Let's extend this axis, okay? This is S of T, okay? Now, the same way. Now, for us to be able to achieve amplification, then it means that beta has to be greater than 1. And for us to be able to achieve attenuation, then beta must be less than 1. It's about the same idea. Now, if beta is greater than 1, so let's say S of T goes into a system for which beta, for which beta operates on the signal, this time amplitude, where we have Y of T is the same as beta S of T. Beta S of T. Now you'll observe that beta multiplies the entire signal and not the time scale. Okay, because we are actually trying to manipulate the amplitude of the signal. Okay, now if beta, okay, go ahead, Julius or Joe.
Sorry, sir.
Go ahead, please.
That previous slide, I wanted to ask if that time reversal, that beta equals to -1, can it also be like the since -1 is also less than 1, can it also be like time like signal compression?
Time reversal and compression are two different operations. Now, you mean -1/2, right? So is it possible to have both reversal and compression at the same time? I'm sure that's what you're trying to say. Is that what you're trying to say? Is Ojo still with us? Ojo? Okay, well, we can't hear him anymore. Well, if the operation on the signal, if the system operates on the signal such that we have, say, S of t is fed into the system, and then we have y of t such that beta is the same as -1/2. So it means that this is going to also perform reversal, because this is the same as saying beta is the same as -1 times 1/2. So it's going to perform both operations. Is that clear?
I'm so confused.
Yes,
Okay,
sir.
what's confusing right now? So tell me. So let's clear all doubts.
You said that if you said that it performs both expansion and compression. I'm so lost.
Now this is, well, we are not on amplitude anymore. Ojo just took us back to time scaling. So we're not on amplitude scaling right now. Okay, we are back to time scaling. Now he said, well, the -1, well, I tried to clarify, we couldn't hear him anymore. His hands are still up, but I don't know. That the -1, could it also be compression? That was the last thing I heard from him. Now, by the time we multiply the time scale by -1, we are literally flipping the signal over. Okay, we are reversing the signal. So it means that the signal is folding over the amplitude scale, okay, to the other side. So it means this signal is flipping over this S of t axis to this other side. That's all it does. But is it possible to perform multiple operations on the signal? Yes. So let's assume beta, which is the parameter in this case, performing this operation on the time scale. What if it is -1/2? Now, we already mentioned that if the value is less than 1, we are going to get a compressed signal, because it's going to be dividing the time scale by that value, right? So it means that if beta, for instance, is not a positive value, but yet less than 1, meaning it is -½ So we can also disintegrate this to say, well, this is the same as -1 times ½ So it means that it is going to perform both reversal and compression.
So, sir, in essence, it's a reverse compressed signal.
Exactly.
Okay.
Is that clear?
Yes, sir.
Yeah, and that's just, that's that. So I hope we just answered what he wanted, but unfortunately we couldn't hear him again. So maybe network issues. So okay, so we come back to our amplitude scaling. Now, so let's assume we want to scale the amplitude. So I think I need to switch this signal to a better place. So let's position it this way. So let's assume this is my scale. Oh, let's use a straight line. So let's say we have this, and then we have this. Now I already have this signal, this and this, okay? So this is S of t, this is t, and this is 2, this is 2. So the time scale here is reading 2, the amplitude is 2, okay? The signal amplitude. And then this is the origin. Now, we are not particular about the time scale this time. So let's say beta is the same as 2, and then beta is the same as 1/2. Okay? So it means that S of t is going to get into a system such that y of t will give us 2 S of t. That's for amplification, okay? amplification. So for attenuation, it means that S of t gets into a system, and then we get our Y of t being the same as S of t divided by 2, right? Because beta is 1/2 when Y of t is the same as beta S of t. So Joshua, tell me.
So I wanted to ask if this same attenuation is the same thing as compression, since we are using beta is equals to 1/2.
No, attenuation is not the same as compression. You know, that's why I try to clarify. You know, if you recall, just before I wiped it, I said, well, when we perform time scaling, we do compression and expansion. Okay? So now the attenuation looks more like the compression of the amplitude, but it is not signal compression in the strict sense, because we only compress about the time axis, okay? So we have this is a signal we want to transmit that is taking the spread. But if I truly compress the signal, I'm going to retain the same amplitude, okay? So let's assume the amplitude is on this dimension, the amplitude is on this dimension, right? Okay, so if I should compress this signal, then it means that all of these, 1, 2, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it means that everything 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah. So everything is now within this range. You get that? So it means that this entire signal that would have taken a wider bandwidth is now taking it's not taking smaller bandwidth because of compression. But the amplitude scale is the same. Okay, the amplitude scale is the same, but I've only compressed it over time axis. So it's different from attenuation. Okay, because with compression, I cannot experience loss of signal. But with attenuation, I can experience loss of signal. Okay, Rotimi, tell me.
Sir, are you saying that during compression of signal, no signal is lost? It just, compressed.
Now that's what I just said. So you want to tell us something else?
So the signal that is compressed or extended, is it with regards to the amplitude or the time?
It's relative to the time.
Okay, sir.
Yeah. On the time axis, yeah. That we are compressing or expanding. Yeah. Okay. Is this clear? Is this clear?
Yes, sir.
Okay. So let's wipe this and go back to our So let's go back to our amplitude scale. Okay. Now, so for amplification, we want to achieve this, so 2s of t. What's the amplitude? Is 2. So 2 times 2, that's 4. So it means this is coming somewhere here. So for amplification, a signal is going to look something like, oh no. It's 4. So a signal is going to look something like this. You see that? So this is amplification. We've been able to amplify the amplitude. And we do this especially when we want to transmit over a long distance. So we have repeating stations, okay? More like in your broadcast stations, we have repeating stations. Now, the signal can travel relative to the wavelength and the frequency, right? Because they are inversely proportional, right? So when the frequency becomes very large, it can travel shorter distance. So when the frequency is smaller, it can travel further distance. So that is why most of the time in our regular mobile communication, we use the lower frequencies for coverage to communicate over a wider range. You know? And then we now use the larger frequencies to optimize for capacity, because we can only cover very shorter distances. Okay, so when we attempt to use such frequencies, what we do is to have repeating stations so as to always amplify, because the signal attenuates as it travels. Okay, that's why you get to some place say there's no coverage, because the signal, due to signal attenuation, there are a lot of factors that leads to that. Okay, could be interference, large scale or small scale fading, whatsoever you may call it. So there are a lot of factors within the communication domain that can actually attenuate the signal, such that as it travels over time, it loses its strength and its power. So if you still want to make use of that signal, you may want to have a repeating station to trap the signal, then increase its transmit power, and then push it out again. So you push up the amplitude, okay? So alternatively, we may want to achieve attenuation. Then it means that we are multiplying by a parameter that is less than 1. So let's say half. So it means that we are going to be having something like this. So let's say this is 1, right? So 2 divided by 2, that's 1. So we're going to be having a signal come somewhere around here, half of it. So this becomes the attenuated signal. So we can continue to attenuate this signal till it gets to a 0 zone where there's total loss of signal, okay? So this is what it means to perform amplitude scaling. It's quite theoretical, but I just explained the application, okay? And there are times we may want to, attenuate the signal, or better say cancel it out. So you talk about interference. You must have heard that, the word interference. Okay, and let's say simply we could have constructive interference or destructive, okay? Destructive interference, such that signals could interfere such that if it is constructive, then it means their amplitude power or signal power adds up. But if it's destructive, it means they cancel out. So somewhere here, around here, so they cancel out. So at this point, it's a 0 zone. It's a 0 zone, right? They're canceling out here. There's nothing, you can't really get any point in here. That is why even in the communication system where you have your mast and your band antennas and your microwave antennas, these are for transmission, right? Transmission. You must have seen them, why these are for coverage, right? Now, when you come under the base station, you are not expected to receive any signal because we call that the 0 zone. Okay. Well, let's leave that for your future classes. I think at this point, is this clear? Is this clear?
To an extent, sir.
Okay, to an extent. Okay, that's encouraging. So let us do amplitude reversal. Okay, Kelvin, tell us.
Hello, good afternoon, sir.
Good afternoon.
Yes, sir, I have a little issue. I don't really understand the time scaling. the one about an audio file of increasing the time scaling to about 2 times seems to doesn't compress it. I don't know how to put it a bit. But the one of time scaling is a bit different from what I already know a bit, sir. So can you please clarify it?
Okay, well, I'm yet to understand your question. My apologies. So can you
Okay,
please
sir.
explain in a way in a way I understand?
Okay, sir. So what I meant was that in time scaling, x of 2t
Okay,
is supposed to be
let's wipe this. S of 2t
is supposed to be like compression,
okay.
not amplification, sir.
Yes. S of 2t is supposed to be compression, not expansion, right? Beautiful. Now, in the previous video, I said beta is the same as 1 over p, right? So that when p is equal to 2, then it means that 1 over 2 is beta. So this is going to give you compression, right? So that when p is the same as 1 over 2, then beta being the same as 1 over p will now be 1 over 1 over 2, which will be the same as 2, which is the same as 2, right? And now this will be 1 over p equal to beta equal to 2, right? But now I did not play with this definition. I just gave you beta. Okay. So I know you've been following up on the previous video. So that's what you're looking at now, right?
Yes, sir.
So, but we are doing the same thing.
Okay, I understand, sir. Thank you, sir.
Yeah. So the bottom line is the parameter that scales the time, should it be greater than 1? What do we get? Should it be less than 1? What do we get? Okay. So I think it's in the definition now. So I just posed a slightly different definition to get the same result this time, right? Is that clear?
Yes, sir.
Okay. Okay. So let us go to, we've done amplitude scaling. So the same applies for amplitude reversal. So the same applies when we talk about amplitude reversal. So same way, beta is the same as -1. So if we have the amplitude this way to s of t, now where s of t goes into a system where beta is the same as -1, where beta is the same as -1, then y of t is going to give us negative s of t, right? So technically, by the time we multiply the amplitude by negative, so it's going to give us -2. So it's going to show up somewhere around here, all right? Isn't it? So it means it flips. Does that make sense?
Yes, sir.
So it means we are flipping it. So it's not going to flip this way, -2, so it comes this way. So that's more like amplitude reversal, okay? So let us go now way into the more interesting part, okay? Which is the time shifting. I know I made mention of this in our last class, one of our classes, when we talked about time advance and and time shifting, delay and advance, right? Rotimi John, please tell us.
So when it that should please come again. I didn't get that part.
Which part didn't you get?
Like I mistakenly logged out and logged in back. That's why. So I'm confused at the diagram I'm seeing.
This particular diagram?
Yes, sir.
Okay, this is amplitude reversal. You know, I'm sure, hope you were not logged out when we talked about time reversal.
No, sir.
Okay, the same principle applies. Beta is the same as -1, but this time the -1 applies only, or better still, manipulates the amplitude and not the time scale. So we have S of t going into a system defined such that beta is the same as -1. And now this only have impact on the amplitude such that y of t is the same as -S of t. So when we multiply the amplitude signal by a negative value, so that will give us -2, right? So
yes, sir.
That flips the signal over the time axis. So the signal is folding over the time axis. So what we now have is, what do we call it now? The amplitude reverse signal, right?
Yes, sir.
Yeah, so that's
Thank
it.
you.
You're welcome. Okay. So now let us look up time shifting. Time shifting. This is very, very important in signal processing because you want to play with storage. You want to play with database. Yeah, even biometric systems. Want to play with biometric systems. Then you want to play with signal transmission. Okay, signal transmission. So oftentimes you hear of things like latency, time delay, and all of that. So it all comes, you know, under this time shifting idea. Now, when it comes to your storage database and most of the biometric systems, you actually have an idea of the output. Okay, let's talk about your machine learning. You have your data, your training data. So you now have to split it into your validation, test data, and all of that. And then you get something that looks like it. Then it begins to train. To say, well, let's match it with what we have. Perform some feature extraction, you know, and all of that. And then says, well, this is what it is. This is the face of this guy. But mind you, you already saved the face of the person. Probably you want to use your, you know, fingerprint and all of that. You already recorded it. So you want to open up your system with your fingerprint. You already saved it to the system. So when you try to open up, you don't want to use password and you place your fingerprint on it. So it's going to match it with what it has. If there's a mismatch, it won't log in. Now, what you're actually doing is that you already received the output before you transmitted your inputs. Okay, because you already saved up the outputs. That's what happens in storage, in database systems, biometric systems. But when we talk about real-time communication, now what we are doing right now, I'm talking from one location and you are receiving at another location, but you really cannot tell the time delay. But the bottom line is you do not receive my voice signal instantaneously. There's some time delay. Yeah. So it means that I have to transmit before you receive. So there's some level of delay. Okay. So when we talk about all of this storage, blah, 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 we talk about time advance. Okay. Let's put it this way. We talk about time advance. Now, when we talk about our real-time communication system, we talk about time delay. Okay. Okay.
Okay.
Okay. Now, so we are going to play with both. So when we talk about,
okay.
I think someone is talking to us. Is that Ojo? So let's hear him out. Ojo Tolu Lokbe, right? So tell us.
I'm sorry, sir. It's not you, sir.
Okay. So now, we now have two parts to this. Time advance, which we also refer to as left shifting. Then we also have time delay, which we refer to as right shifting. Now, so I want to say, well, when the signal shifts to the left, it is time advance. So it's like we are thinking using a reverse mode, but not necessarily. So we're going to clear it all up now. I know there was a question that triggered this in one of our classes. So this is the time scale, right? So this is negative infinity. This is positive infinity. So this is our amplitude scale, the signal scale, okay? Now, it means that I literally move from some -3, -2, -1, 0 to 1, 2, 3, all the way, okay? So if I should transmit, say at time t equal to 2, if it is time advanced, then it means that my signal is going to come this way. It's going to shift to the left, okay? But if, for instance, I transmit at time, let's change the color so we don't get this mixed up. At time t equal to 2 also, and then my signal moves to the right, it is delay. So this is delay. This is advance. Does that make sense?
Yes, sir.
Okay. So technically, we now say that signal advance is represented as the positive of the time scale, t plus beta. So it means that if S of t is fed into a system characterized by some parameter beta, then it means that our output will be the same as S of t plus beta, right? Now, if it is signal delay, it is characterized by t minus beta, such that S of t fed into a system characterized by beta will give us y of t being the same as S of t minus beta. Now, beta in this case is some t sub k, okay? Some time parameter. Hello?
Yes, sir.
So we can liken
Yes, sir.
t sub k as some positive time parameter and beta as some negative time parameter. So let us play with an example, okay? So, okay, let us play with one simple example. This is time shifting. So, well, a regular example, this is 2, this is 0, S of t, t. So let's assume that beta is the same as +1, and beta is also the same as -1. So what are we going to get here? So we know that S of t for beta being the same as +1 is going to give us time advance, right? So this is fed into a system for which beta is the same as +1. And then we get our output, which is the same as S of t plus 1. Right? Is that clear, please?
Yes.
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
Okay. So now we are going to work on this to know how to plot our output. So we now start with our time axis. So initially, what we have is at t equal to 0, right? At this point. So let's move that way. So this now is going to give us this parameter, which is S of t plus 1, right? Isn't it?
Yes, sir.
Good. So it means that if we extract our time activities here, because this is S of t equal to 0, then t plus 1. So it means that t equal to 0 is the same as S of t, or is the same as t plus 1, right? So technically, we can wipe this and say 0 is the same as t plus 1. So what is t? T will be the same as -1, right? At this point. Is that okay? Is that clear?
No, no, sir,
Yes,
it's not
sir.
clear, sir.
Okay, I was expecting that. Okay, now let us wipe this. So how we arrive at the time advance. So this now, I'm going to change this to beta, right? This is what we have. So it means that S of t is going to give us S of t plus 1. Isn't it?
Yes, sir.
Yes, sir.
So let us knock off, what we're interested in is our time axis. So let us knock off x. So what do we have? T is going to give us t plus 1, right? So this is our input. This is our output, right? So what we are after is the time we are going to receive this in the output, not input. But we know our input time values. In this case is 0 and 2, but we don't know t at the output. Does that make sense?
Sir.
Yes, sir.
Okay. So if t is the same as 0, for instance, we want to work on the time axis now. If t is the same as 0, this is input value. So what is going to be t at the output? So make t subject of formula. T is equal to -1, right?
Yes, sir.
Good. So let us play with the second. So when t is 2, so we'll come back. T tends to t plus 1. So when t is 2, this is input, this is output. So what's going to be t at the output? So
1.
t will be 2 minus 1, which is equal to 1. T is equal to 1. So it means that we now have to rescale. we now have to rescale. So this is 1. Then this is -1. Let's clear this 0 out. 0 should be where it should be. It's this 0 here, right? The origin. So why this is also -1. So it means that when t is 0, we have the amplitude here to be 2, right? So it shifts to -1, right? Do you get that? The amplitude
Yes, sir.
remains. So
Yes, sir.
it shifts to this point. So when t is 2, the amplitude, which is also 2, shifts to 1. So you see, the signal just shifted to the left, right?
Yes, sir.
This is the original.
Yes, sir.
This is the original signal. Now you can see that this is the input, and now this is the output. So you can see that the output is occurring in the past time, not in future time, which is not realizable in real-time systems. Does that make sense? Now,
Yes, sir.
your time axis is more like this is the past, this is the future, right? So what we have here is the present time. This is what we are dealing with right now. That's the signal we are dealing with right now. So it's either it moves to the future or it moves to the past. But now our signal, which we transmitted in the present, is occurring in the past. Is that realizable in real-time systems? No.
No, sir.
But is it realizable in real life?
No, sir.
Yes.
Yes.
Yes, sir.
Yeah.
This is time advance.
This is time
When we
advance.
spoke about biometric this thing.
Exactly. Storage. Okay. When you save your when you do your machine learning, you say data, I need data. Then after that, you now begin to extract your data for validation, for testing and all of that, to train. Then you want to do image processing, you want to do computer vision and all of those. So you are saving up your output really, which you will use to train, or let's say biometric, your access technique, okay? Your fingerprint, you get to the office, through your fingerprint, you are able to open your door, access to your office. You must have saved your fingerprint before coming in. So your fingerprint is already saved up in the database. Okay, so when you now plug in so it tracks it to match it. So if it matches, it opens. The same thing with your devices. Some of you use iPhone, use biometric, you use your eye contact to open up your phone and all of that, right? Facial recognition and all of that. The same thing, okay? It does some feature extraction and all. So when we try to play with storage systems, yes, fine. Our output could be in the past, so this is what we call time advance, right? So while we're just transmitting the present to extract what is in the past. Is this okay? Is this clear? Is this clear?
Yes, sir. Yes, sir.
Okay. Okay. If you just said so, then that's fine. We are good to go. So I think the same applies. Let us look at the time shifting. In terms of delay, time shifting. So now we want to consider signal delay. So we'll play with the same example. So we have the signal, S of t, this is 0, then this is 2, then this is 2, right? So, so let's take S of t, it goes into a system described as beta being the same as -1. Okay, so let's not, then we have our output y of t, which is the same as s of t minus 1, minus beta. No, not minus beta. It's going to be plus beta, but this time it's going to be -1, right? -1. Because, yeah. Okay, now that we have this, so it means that we have s of t will give us s of t minus 1. Like we mentioned earlier, this is our input and this is our output. Okay, so it means t is going to give us t minus 1. So when t is 0, we have t minus 1. So t is equal to 1, right? And when t, 10 to t minus 1, when t is 2, we have t minus 1. So that will be, t will be the same as 2 plus 1, which will be 3, right? So it means that when we transmitted this signal at time t equal to 0, the signal experienced a delay for time t equal to 1, right? So this is what was transmitted at the output. Okay, and then it went on this way. So at time t equal to 2, it went on to 3. So you can see the signal is actually occurring at a later time in the future. So this is signal delay. So it's more like I transmitted at 1 p.m., then I received the signal at 1:05 p.m. That's what is happening here. Transmitted at 1, at 2, we are getting at 3, right? So just speaking in the loose sense of it. So this is our input, then this is our output. So this is input signal, and then this is the output signal. Is this clear?
Yes, I have a question.
Go ahead, please.
In the last class, you taught us about linear time invariant systems. If I strike a key on my keyboard, is the keyboard produces the letter on the screen. Can I call that system a time invariant system?
Okay, you strike a key on your keyboard, then it gives you the output, right? Is it,
Yes, sir.
Is it a linear time invariant system? So, well, you're taking us off this now, but I'll quickly attend to that. So what is linear time invariant system? LTI, right? So it is linear. It is time invariant. So it means that the output of the system is not altered regardless of the time of transmission. So if I should punch B on my keyboard today, I'm going to get a B. If I should punch the B 5 years to come, I'm still going to get a B. So it means it is time invariant. Now, linear, is it linear? So the output and input, do they obey the law of the superposition principle, where we talk about scaling, homogeneity, and the likes? So technically, we can say, well, it models an LTI system. But do we have a perfect LTI system? No, because your system could malfunction and pose some level of non-linearity that may not make it linear, okay? Due to aging, circuitry issues, at times it could overheat and begin to misbehave. You could even punch a button and it doesn't respond. You could punch H and it just begins to punch the H infinitely and doesn't stop. So at that point, it's not behaving as a linear system. So, like I said earlier, in practice, we do not really have absolute linear time invariant systems. It is more like an approximation, an ideal approximation for practical systems. Is that okay?
Yes, sir.
Okay. So can we progress now? Still have a few things to
Yes, sir.
cover. Okay, let us. Okay, so I think we are done with this. So let us do amplitude shifting. Okay. So let's do amplitude shifting. So let's assume we have a signal. This time we want to shift the amplitude. So we can either shift it upward or downward, okay? So, so if we want to shift a signal upward, what do? We multiply by a positive value. If we want to shift it downward, we multiply by a negative value. So technically we use DC to shift our signals most of the time in practical systems, okay? But let us play with what we've been playing with before now. That is 0, 2. Excuse me, S of t, t. So let's assume beta this time is the same as say +1. Or let's say, do I want to use positive? Let's use +1. Or it is the same as -1. Okay. Now, okay, let's see the impact. Let's make it 2. Let's see the impact. I want us to see the impact on the signal. Let's increase the magnitude. Let's increase the magnitude. +2, -2. So the amplitude this time is also 2. So if we feed this into a system, S of t, say we're a beta parameter, then we are going to get y of t being the same as 2 S of t positive, right? And then the same with this, S of t for beta will give us y of t, which is -2 S of t. Now, okay, coming. There's something here. Let me clear this. Because we are playing with DC this time, right? DC, like I mentioned earlier. So that will not be a proper representation of the shifting. But we need a DC. So it means S of t, for which beta value will give us y of t being the same as S of t plus beta. This is what we have. Because at this point, beta is a DC value. Okay? So it means that it could be positive or negative. So S of t will give us with the parameter +2, which is the same as +2, is going to give us y of t being the same as S of t +2. That's when beta is positive. Then S of t be the same as beta being the same as -2 will give us y of t being the same as S of t -2. Okay, so this is it. So what do? We use the DC signal to shift the amplitude, okay? So we either shift upward or downward. So if it's a positive value, let's say +1 or +2. So it means that at 0, by the time we add 1 to 0, so for the positive shift, 0 plus 2, so it means our signal now comes this way. Let's say this is 2. 2 plus 2 is now 4. So it means our signal is going to shift this way, where this is also 2t. Now, for downward shift, when it is negative, it's positive. When it is negative, so 2 minus 2 is 0. So it means this point is not going to come to 0. Not going to come to 0. Then 0 minus 2 is coming to minus 2. So minus 2. So this is going to come this way, where this is 2. See. So you now see that with a DC applied to your signal, you can either move the signal forward, upward, or downward. So we call this upward shift, and then this is downward shift. Upward shift, then we'll call this downward shift, right? Now, is this clear?
Yes, sir.
So
No,
I think,
sir.
okay, no, yes, okay, fine. Now, for your amplitude shifting, it's not amplitude scaling. So if we're scaling the amplitude, we multiply it by it. But if we want to shift it, then it means I want to add a DC value. Now, a DC value is just a constant value. Okay, remember we said a DC is not a signal. Okay, it's just a constant value. So it means that here we have added a DC value of 2 such that that DC value just runs this way. So here there's a DC value that is just, running all the way on this axis. So it means that that DC value becomes the more like it is the axis. Sorry, this one is coming under the DC value running that way. Okay, this positive to this negative 2. Okay, so that DC value is now forming the new axis. Okay, so with the DC value, we are able to perturb or shift the time scale. Okay, so we do that when we are trying to manipulate some signals in practice and all of that. And probably when you begin your lab activities, you are going to see some of those things in the spectrum analyzer. Okay, how the signal shifts. So what have we done here? We just added a DC value, beta. Okay, so this is signal, but now we have added a DC value of 2. So that is what we have here. So that helps shifts the signal. So every other thing about the signal remains the same. Now, for the negative, we just shifted the signal downward as well. Okay. Okay. Now, I'd love to mention just one thing to wrap up this signal manipulation. And that is waveform representation, okay? Now, when it comes to signal representation, we want to generate the waveform for signals. Conventionally, we can use unit step functions and ramp functions to represent, signals, okay? Or better still, to design the signal waveform, okay? I will know that our unit step function is something like this. It just comes this way and it steps, right? While our ramp is something like this, it just spikes off to infinity, okay? So we say this is U of t. This is R of t, okay? And the U of t takes on values from 0, this t, the 0, this t, takes on values of 0 at time less than 0. So everywhere before 0, so negative infinity is 0. Then it takes on the value of 1 at time t greater than 0. So the time axis greater than 0, all the way it's 1, okay? Now, for the ramp function, r of t, it takes on a 0 value, so now it's 0 everywhere else at t less than 0, and it takes on the value of t at some time greater or equal to 0. So this t, okay? And if that is that, so it means that this is 45 degrees, so that the gradient here is 1, which is the same as tan 45 degree, right? Okay. Those are your regular mathematics. Now, we know that for us to be able to derive our ramp function, all we need to do is to integrate our unit step function. And for us to be able to get our unit step function, it follows directly that you differentiate the ramp function, okay? So let us try something out. Let's play with this. So we have a signal. So this is 1. So this is negative infinity to some time t, okay? Now, for us to be able to get the ramp function, so we want to integrate this unit step function. So it means r of t is the same as taking the integral negative infinity to t, that's the time limit, from negative infinity to t. Then we know this is u of t dt. Now, we know that we can also disintegrate this expression from negative infinity to 0 and from 0 to t. So we can take the integral from negative infinity to 0. The value is 0 dt, plus the integral from 0 to t is 1. That is 1, right? dt, because the magnitude is 1. So this reduces to 0, so there's nothing to integrate there. So if we integrate this, if we integrate 1, it's going to give us t, taking on values from 0 to t, okay, which is the same as t. And that is a ramp function, t, at some value greater than this, so that r of t, which is the same as r of t, which validates what we just placed here, right? So we can now say that t times 1 is the same as t. So we can now say that the ramp function is the same as t u of t, since u of t is 1. Okay? So I need you to take note of this. Now, if the ramp function is the same as t u of t, so if this signal should experience some delay, r of t minus t sub k, now you know that time delay is represented by a negative, right? If it's positive, it's time advance. Then it means that t minus t sub k u of t minus t sub k. This is what we get. So if there is time delay for this signal, so it means that all the time components will experience the same amount of delay. Now, this is going to be very, very, very important in our representation of signals, okay? Now, let's give a little rule, a little ground rule, okay? The basic rules for representation of waveform, basic rules for waveform representation. I'll just run through this quickly. So one, we want to use positive sign for upward turn. Then you also want to use negative sign for downward turn. Now, The next thing is the ramp function is represented as the product of the magnitude of the slope and the ramp function.
You have low attention span.
So here we take time delay into consideration, okay? And then the fourth thing here is that
that's a stop.
Joshua, is there anything you want us to do for you?
Sir, I wanted to ask why do we shift the signals?
Why
do we do signal shift?
Well, you'll see that shortly. Now, the step function is represented by the product of the magnitude difference at the point of discontinuity. Now, this is just the rule, okay? So now I'm going to play with a simple example. So let's assume I have a waveform that looks something like this. Okay? This is the waveform. And here we have 4. Then this is T. And this is S of T. So we say, well, represent the signal with the unit step function and the ramp. So what do we want to do? So we'll begin to trace from left to right, okay? So this is how we begin our trace. So let's start. We begin to trace from this point. So what we get here is 0. So we trace that all the way, right? So we have 0. Let's put it here, 0. S of T is equal to 0. Now it says when we get a positive sign or upward turn. So now this graph goes upward here, but this is a 0 here, upward. So for us to go upward, this is upward. For us to go upward this way, it's a positive. So that's positive. And now this is a slope. So it's going to be represented with a ramp. And we're going to get the magnitude of this slope about this point. Now the point of rotation is the time of reference. Now the slope is going to be 4 minus 0. Then what is this? So let's say this is 2, for instance. 4 minus 0 divided by 2 minus 0. So that's going to be the slope. So we take the slope, 4 minus 0 divided by 2 minus 0. Then we multiply it by the ramp function, arrow of T. The time of reference is 0. That's the time delay, minus 0. So it keeps going indefinitely. But now we need to come down because there's a unit step function here. So for us to be able to take this down, so it means it needs to come downward and then go all the way, right? So let's use another color for that. So let's say it comes downward and goes all the way. Now you see that this angle and this angle are corresponding angles. So it came down. So now we use a negative sign when it comes downward. So that's going to be minus. Now, since they are corresponding angles, it's going to be the same slope, 4 minus 0 divided by 2 minus 0, times arrow of T. Now, this arrow of T, the point of reference is 2, not 0 anymore, minus 2. Now, we are still going to take it downward because from this point to this point, where we can get our unit step function is still coming downward. So that is now negative. Now, for this, the difference of the magnitude when we consider the unit step for the step function will represent the product of, will represent it by the product of the magnitude difference. So that will be 4. The magnitude is 4 to 0. 4 minus 0, 4 minus 0, times the unit step function t at the time reference minus 2. So this unit step comes like this and goes all the way. So that is that. So once we extract this, so this will be 4 divided by 2, that is 2. Let's change the color to black so it becomes more visible. 2 arrow of t minus 2 arrow of t minus 2 minus 4 u of t minus 2. So this is the waveform representation of this plot, okay? Now, I think in the channel, I got a message, was it last week or so, that can all signals be represented using ramp function and unit step function? Well, the answer is obviously no, because certain type of signals cannot be analyzed using the unit or the step function. So we may want to use sinusoidal or exponential signals to represent such signals, okay? So I think, well, this is a good place to stop. We are just right in time. Any question, please? Go ahead,
Yes, sir.
Ebube.
So the signals represented with waveform representation, are they always continuous signals?
Well, definitely, these are continuous signals. These are continuous signals.
Okay, sir.
We are playing with here.
Thank you, sir.
Okay, sir, I asked that why do we shift signals, sir?
Okay, why do we shift signals? Do we really shift signals? I don't think we shift signals. Signals just shift. How do I mean? Now, you just asked a question. Why do we shift signals? And trust me, I did not receive that voice note instantaneously. So it shifted in time based on propagation activities, okay? So what we are trying to do is to idealize or provide an abstraction of what happens in real life, okay? So we know that there is a delay in the process of signal transmission and reception. So we just try to model it. Is that okay? Is that clear?
Yes, sir. Thank you, sir. Thank you, sir.
You're welcome. So Isaac, tell us.
Good day, sir.
Good day.
I want to make reference to the last class when we were talking about energy.
Okay.
I think maybe it's because of time was not on our side. So I want to talk about this discrete time signal. It didn't give us how discrete time signal can be assessed, whether it's an energy signal or a power signal. Because in your video, when I looking at the examples on discrete time signals, I was confused.
Okay. So don't worry, we'll play with that maybe in our next class. Now, whether we are playing with discrete time signals or continuous time signals, the whole rules apply. Okay. Now, discrete time, continuous time, they are just different ways of interpreting same signal in different plane, either in the analog or digital plane. Is that okay?
Yes, sir. But for continuous time, you use integration. Why for discrete time, you use the sigma?
Yeah, we use summation. Now, summation, now integration is the same as summation. It's just that the integral is used in the continuous domain, while the summation is used in the discrete domain. They perform the same operation. Is that okay?
No, sir.
Okay. Now, though we are running, we already are, we are out of time already. Now, this is what I mean. This is integral. This is sigma, okay? This is summation. Now, I'm now telling you, we use this in the continuous domain, while we use this in the discrete domain, but both perform summation. Because we are taking over a range, say x1 to x2, okay? We're also taking from a range x1 to xn, okay? So at this point, we are trying to check, let's say this is a graph. So we are trying to check the area under this graph. And now, this is also the graph. So we're also trying to check the area under this graph. So the area under this graph is the integral of whatsoever we have here. That gives us the area, which is the sum of what is happening here. And this sigma also provides the sum of what is happening here to give us the area under the same graph, which has been discretized. So this signal and this signal are the same. Only that at this point, I took just some points of it, this point, and this point. Then probably this point, and this point. Then if we draw this point, and probably, let's say, this is longer, and this point. Okay, so this is a discrete equivalent of this continuous signal. But should I take the summation of these parameters, I'm going to get the area under this graph. And if I take the integral, I'm going to get the area under this graph. So that within the continuous and discrete time domain, these operators perform the same operation. Is that clear?
Yes, sir. It's
Yes,
clear.
sir.
Yeah. But it's just that in the continuous time, I can't use sigma, I use integral. So tell me, please.
Yeah, like for example, x of n equals to minus 0.5 all raised to n u of n. Now the question is, check if this is an energy signal. So can you
Okay. Okay. Yeah, you must have seen all of those in the previous videos, right?
Yes, but I did not understand it at that moment.
Okay, so we'll walk around that next time. Don't worry. Probably we'll play with some examples, okay? I think we are 7 minutes ahead of time already, and I need to jump into another meeting, okay? So we'll play with all of those. Nothing to worry about for now. I think you are doing the right thing, okay? Is that fine?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So do have a great day. We'll see you next class, okay?
And you, sir.
Bye-bye, sir.
Goodbye.
Thank you, sir.
Bye-bye.